Hello all, welcome back. So in this today's class, we'll design SR flip-flop operation, right? So in previous class, what we have discussed is that, so how to attach the clock pulse to the latch we have done. So after attaching the clock signal to the latch, then it will become the flip-flop, right? So that is what we discussed in the previous class, right? So now what we will do in this today's class is that the first thing is that we will draw the, right? So SR flip-flop block diagram, right? So block diagram of the SR flip-flop. So once it is done, so from the block diagram we can able to identify how many inputs we require as well as how many outputs we require, that we can able to find. Once it is completed, we will draw the truth table of the NAND logic gate, right? So why NAND logic gate means here there will be having the some logic, right? The same logic which we explained in the SR latch as well as the RS latch using the NAND NOR gate representation, right? Once it is done, we will draw the circuit diagram for the SR flip-flop, right? So once it is done, finally we will draw the truth table operation, right? So once we will draw the truth table operation, so finally we will write the characteristic equation. So these are the things which we are going to study in the today's section, right? So first we will draw the SR flip-flop block diagram representation, right? So now if you observe here, right? So SR means two input terminal, right? So if you consider the block diagram representation, so we have the two inputs, right? So this is what we called as the SR flip-flop, right? So SR flip-flop. So how many inputs we have? One is the S, another one is the R, right? So how many outputs? As we know that the flip-flop will be having the two outputs. One is the normal output, another one is the complemented output. Now if you observe here, this is latch or flip-flop. Try to pause the video and try to find out the answer. This is still latch, right? So in latch also we have the same representation, right? But what is the additional thing will be there in the flip-flop? So here we will be having the something called as the clock pulse operation. Clock pulse or enable we can consider. So clock pulse is something different. There we have to take the edge triggering, positive edge, negative edge. Later on we will discuss that part. So here one more input is the clock signal value as well as the enable value, right? So in drawing the truth table, I am not going to consider the clock signal. The reason is that when clock equal to 1 only, the operation will be work as the flip-flop. Else it will work remain same as clock absent means it will work same as the latch only. When clock equal to 1, it will work as the flip-flop operation, right? That one point you have to remember. Once it is done, so block diagram is completed. So three inputs SR clock, outputs are qn bar, right? So first how to remember this block diagram, right? So I have seen that people are finding difficulty in order to draw this logic diagram. So I'll try to explain in the simplest manner how to draw the logic circuit diagram. So how many inputs we have? Two inputs, right? So if you have the two inputs, you just try to take the two NAND gates, right? So first NAND gate 1, then one more the again NAND gate 1, right? Now if you observe, this is a combinational logic circuit, right? So output is completely depends upon the input value. It means that it is the combinational logic circuit. Now what is our duty is that somehow we need to convert this combinational logic circuit into the sequential logic circuit. So for that reason I am going to connect this output to input, this output to input, right? So we will be having the two outputs qn as well as the qn bar. So one of the input terminal. Now if you observe this one, this is not flip-flop, that is only latch. So for what is called as flip-flop, for latch we need to add the clock signal mechanism, right? Now we'll try to add the, this is the latch, for this latch we need to add the clock signal mechanism, right? I have explained in previous classes how to design the clock signal, what is the requirement of designing the clock signal, everything I explained. So if you don't understand, please go back to the previous video so that it will be easy for you to understand this particular lecture, right? Thank you. Now see that, so this is my clock signal, right? So for that what I'm going to do is I'm going to add the extra clock signal, right? So minimum number of inputs 2, right? So this one I'm going to commonly collected nothing but the clock. This input value is yes, this one more input value is there, right? This we are going to take as the R. The same diagram which is here, which is nothing but this one. So this is how we need to draw the logic circuit diagram. If you can able to draw this one, then remaining flip-flops are the same circuit. You will be having the some simple modification, right? So this is block diagram, circuit diagram representation for the SR flip-flop. Now once it is done, what is the next step is that we need to draw the truth table representation. right? So I'm not going to consider the clock, guys. By default clock equal to 1, something like that I'm going to consider. So if you want to consider, you can consider the clock, but there you need to write the edge triggering mechanism, right? So instead of doing that, I'm thinking that clock value equal to always 1. So that reason I'm going to consider the only input values, right? So I'm considering only input values, that is nothing but SRR the input value. So output value is here nothing but the Qn bar as the output value, right? So if you want to meaning, that state meaning we are going to write here, right? So how many inputs we have? 2 inputs. So 0 0 0 1 1 0 1 1, right? Now first, as we discussed as the plan, so first, once block diagram is completed, next we will draw the NAND logic gate truth table, right? So what is the NAND logic gate truth table means, right? So I'm going to consider the input value AB, output is Y. So this is the NAND gate truth table. So 0 0 0 1 1 0 1 1 for NAND gate output equal to 1 1 0, right? So from this, if you understand here we have the 3 outputs are the 1. It means that 3 outputs are the 1 means, see that here one of the input is 0, right? Another input is 0, right? Another input is 0, right? So it means that if any one of the input equal to 0, any one of the input equal to 0, right? So without knowing the second terminal, right? So without second input or second terminal, we can decide, right? We can decide output equal to 1, right? So what is the meaning of this one is, so in some cases, if you are going to find out the output value, you will be finding the situation something like this. You will be finding the one of the input is 0, you don't know second terminal value, even though we need to find the exact output, either it may be 0 or 1, right? So if we don't know what is this exact value also, we need to find the output value. So in order to do that, we require this logic, right? So in RS/ using NAND gate, I have clearly explained. So this concept, or if you don't understand here this logic, you just go back to the previous video, RS/ using NAND gate, so that you will be understanding clearly, right? Right, so from here what you have to understand is that if any one of the input equal to 0, even though if you don't know second terminal value, directly you can decide the output value equal to 1, right? So first, what is the input value we'll consider is the 0 1, right? But later on we'll consider the 0 0 part. First we'll consider the 0 1. Now what is the S value? S value equal to 0, R value equal to 1. As I said that clock value should be always 1, right? Then only it is work as the flip-flop, right? Otherwise it will work as the latch, right? Now if you observe here, what is the input value? 0 1, right? So 0 1 means, according to the truth table, what is the output value? 0 1 means 1, right? Just I'm going to write this value 1, right? Now next, what is the input value? 1 1, right? So 1 1 means what is the output value as per the truth table? 0, right? So let it be, this is the first logic gate, this is the second one, this is the third one, this is the fourth one, right? So 1 1 means output equal to 0, right? Now we have obtained the output for the logic gate 1 as well as the logic gate 2. Now question is that we need to find the final output in terms of the Qn bar. So where we need to find out this output means at the logic gate 3 as well as the logic gate 4. At logic gate 3 as well as the logic gate. But if you observe here, this logic gate 3 consists of the 2 input terminal. So this value, we know that this input terminal is the 1. We don't know this value. It means that this is unknown value. As of now, this is the unknown value. So if you consider the fourth logic gate, this value is 0, this value is unknown value. Now see that in previous case we know 2 inputs, but here we know only 1 input value. Even though if you know 1 input value, we need to find out the output. That's the reason why I have explained this concept, right? What is the concept? If any one of the input equal to 0, even though if you don't know second terminal, directly you can find the output value. Now try to guess for which logic gate we can find the output value. Logic gate 3 or logic gate 4? See, for logic gate 3 we cannot able to find out. Reason is that if any one of the input equal to 1, so this input terminal is mandatory. Without knowing this value, you cannot able to do anything, remember. But if any one of the input terminal equal to 0, if we don't know second terminal value, we can decide the output equal to 1. So it means that for logic gate 4, we can able to find the output even though if we don't know the second terminal value. So what is that output value? If any one of the input equal to 0, output equal to 1, right? Just write 1. As we discussed, if any one of the input equal to 1, what is the mandatory thing? The mandatory thing is that this value is mandatory. But how we can able to get this value? Second terminal is mandatory here. How to get? So see that currently we got this output, right? This output will be feedback to here, right? So like this we are going to get the value. Then we are going to find the output for the logic gate 3, right? So it means that the same value 1, so it will go to through the feedback path. So what is this value? 1, right? So this value is 1. So according to truth table of the NAND gate, 1 1 means what is the output value? 1 1 means 0. Now see that QN value we got 0, QN bar 1. It means valid condition or invalid condition? Valid. So it is storing the complement value. Now, so what is the output value we got? So QN equal to 0, QN bar equal to 1, right? So let me tell you the shortcut. So without doing this value passed into the circuit also, we can able to find the output. Now if you observe here, right? So this is the input condition, right? 0 1, which is activated. 1 means activated. So 1 means which terminal is activated? Reset, right? As we discussed in the previous classes, if reset is activated, what should be the output value? Output shared value should be always 0. See that this is 0. This is the complement of this value. That's it. This is the complement of this value, right? So like that we can also find out. Now for example, suppose say, right, we will consider the one more input condition. So this time we will consider the 1 0. Now try to guess the what is the answer without passing the value into the circuit diagram. What is the value, right? So here which one is activated? S is activated. So S is activated means S equal to 1 means set is activated. Set is activated means what should be the output value? Output value should be always 1, right? It means that here what should be the value is that output value when S equal to activated, output value should be 1. So this is a just complement of the QN value 0, right? If R is activated, output should be 0. S is activated, output should be 1. Now what we will do is, if you have this still the doubt, now we will try to pass this S value 1 0 into circuit so that we can able to find out the what is the corresponding value of Q as well as the Q bar, right? Right. So input value is that we are going to consider the 1 0. So it means that S value equal to 1, R value equal to 0. Now see that we know the two input values, right? For the first logic gate, one of the input is 1 1. According to the truth table, 1 1 means what is the output value? The output value is 0, right? So next for logic gate 2, what is the input value? 1 0. 1 0 means what is the output value? The output value is 1, right? Now if you observe logic gate 3, logic gate 4, we know only single input terminal, we don't know second input terminal value. For logic gate 4 also, we know only single input terminal value, we don't know second input terminal value, right? So even though we need to find out the what is the output of QN as well as the QN bar, right? Now try to tell me for which logic gate we can able to find the output without knowing the second input value. Logic gate 3 or logic gate 4? Yes, the answer is the logic gate 3. The reason is that if any one of the input equal to 0, directly we can decide the output equal to 1 as per this truth table logic, right? So now what is the output of QN? That is the 1, right? For this the second terminal is mandatory, right, as we discussed, because without knowing the second terminal you cannot able to find the output. So this whatever the output we got the 1, this will be given to the feedback here. It means that here you will be getting the 1. Now if you see that we have the two input terminal values. What is that? 1 1. So 1 1 means what is the output value? 0. Now it is valid or invalid condition? Valid condition. Why? It is storing the complement value. See that the same value we got here, right? It means that by default when set is activated, output should be 1. That's it, simple logic, right? Now what is the pending thing we need to find out is 0 0 is pending, then one more is the 1 1 is pending. Fine. Now we'll consider the input 1 1 value. It means that S equal to 1, R equal to 1. Now what is the output for the first logic gate? Two inputs are 1 1 means output equal to 0, right? So here two inputs are 1 means output equal to 0 as per the truth table of the NAND gate representation, right? Now question is that you try to find out for which logic gate we can able to find the output. For logic gate 3 or logic gate 4 without knowing the second terminal. Try to pause the video and guess the answer. Yes, the answer is that for logic gate 3, logic gate 4 directly we can find the output. The reason is that, see that if any one of the input is 0, then don't require the second terminal also, we can decide the output equal to 1. If you see in logic gate 3, logic gate 4, one of the input terminal value equal to 0. It means that without knowing the second terminal also, we can decide the output equal to 1. Now here it is a problem, right? So this is valid or invalid? Invalid. Why invalid? It should be always complement one to another, but here we got the same answer. So this is what we called as the invalid or indeterminate state, right? So remember, invalid or indeterminate state. So what this is called, when R is activated, this is called as the reset state. When S is activated, this is called as the set state, just for meaning here, right? So now what is the pending thing? 0 0 is pending. So let me take 0 0, right? So now try to guess the output. 0 1 means what is the output value? 0 1 means 1, 1 0 means 1, right? Now pause the video and try to find out the answer. So in the next level, we have the logic gate 3, logic gate 4. We don't know second input terminal, but we need to find out the final output value Qn bar. Now how to find out which logic gate will be getting the output value, logic gate 3 or logic gate 4? Try to pause the video and try to find out the answer. Yes, the answer is that we cannot able to find out the either output for logic gate 3 as well as logic gate 4. The reason is that we don't know if one input terminal is 1, the second input terminal is mandatory. In previous cases, we are getting either logic gate 3 value is 0 or logic gate value 4 is 0, so that we are finding the output for 1, then that value will be passing through the feedback, so that we are going to find out the next level output value. But here if you observe, the both input terminals are the 1, it means that second input terminal is the mandatory, right? So in this case, no way we cannot able to find the output value. So for that, as we discussed in the SR latch operation, either using NAND gate or NOT gate, what we discussed, if you remember, right? So we need to make the assumption of the output, right? So assumption of the output value. How many output value? We have Qn, one more is the Qn bar. If you make the assumption Qn equal to 1, it should be 0. This is one possibility, because single input means either it may be 1 or 0, right? This is one possibility. Or one more possibility is that we can take the, so in this case I have taken the 1. Now what I will do is I will take the 0 value, this value. Now what should be this value? 1. Either you can consider this possibility or you can consider this possibility, because there is no direct way to find the output value as per this logic also. Now for example, you will assumption the output. After finding the assumption output, we will be finding the next level output, right? If this one is same, this is called as the no change condition. If some other value, this is called as the toggle condition. We will see that, right? What is the meaning of toggle condition when we are discussing the JK flip-flop operation, right? So either you take this combination or this combination, or you try for both the things, you will be getting the same answer only, right? So let me take this one, Qn equal to 1. So it means that I am making the assumption this is my first level output value, right? So this is my assumption output value. So if it is 1, it should be 0. Now this is connected to feedback, right? This value is connected to feedback, right? So here this will go to 0, right? So here what is this value? This is 1, right? So 1 1 means what is the output value? We are getting 0, right? So 0. So 1 0 means what is the output value? 1. See that the first level output assumption is 1 0. The next level or next state output we are getting the 1 0. It means that we are getting the same value. For Qn bar also we are getting the same value. If we are getting the same value, this is called as the no change condition or memory operation. We will see what is the meaning of the memory operation, right? So this is what we called as the no change operation or memory operation or no change operation, right? So this is condition only somewhat difficult, we need to understand. So here we need to make the assumption, right? So this is the final truth table for the SR flip-flop. This is the block diagram, circuit diagram representation, then truth table operation, right? If you observe here this truth table, the both are equal to same, right? So why these both are equal to same means either you can write like this representation or you can represent this one. So what is the meaning of this one is, just we are considering the 3 inputs value SR Qn, then final output will be Qn plus 1. So what is the meaning of this one is, in the first level itself we are making the assumption, right, at the Qn, then Qn bar is nothing but here why they didn't consider Qn bar means here, but Qn bar is always complement to Qn, right? That's the reason why they didn't consider, only they have considered the single output value, right? So they are going to find out, this is my assumption value, they are going to find out the next level output value, right? So this is one way to perform the truth table operation, right? So if you are going to perform this operation, it will take much time, right? So for that, what I'm trying to explain is that just to find the truth table in the same way. So if you understand this concept, the same thing can be copied over here. right? The same thing can be copied over here. Now we'll see how to copy this one. First we'll try to write the input combination, right? So try to remember, the most of the people will have the doubt here is that here first itself, without using this kind of concept, first itself we are assuming that the qn value some random value 1 0 or 0 1. So after passing this value we are finding the next level output. Based on that we are going to tell either it is no change or reset or set or invalid state, right? So for example, what is the input condition for SR? It may be 0 0, right? So what is the assumption of the qn value? Assumption same unte, either it may be 1 or 0, right? So for that reason I am considering the 2 times. It means that each input, it means that if you are giving the 0 0, the first assumption of the qn equal to 0, it means automatically it will be 1. Or for the same input 0 0, you can take the one more assumption qn equal to 1 or 0. It means that each input we need to write the 2 times, because we can take qn equal to 0 or qn bar equal to, qn equal to 1, right? For input condition 1 1, so what is the assumption? Either it may be 0 or 1. Remember guys, I am not taking the qn bar value because qn is just complement of the qn bar. Again, if you are considering qn bar also in this truth table, it is something look like very much complex, right? So let me write. So 0 0 after 0 1, next 1 0 1 0 means 0 1, next 1 1 1 1 means 0 1, right? Now if you understand this one, the same thing here, right? So first input 0 0, either it may be 0 or 1. The second input 0 1, these two combinations, either it may be 0 or 1. Then third input is 1 0, either it may be 0 or 1. The assumption either it may be 0 or 1. So two assumption means the same input we have to consider for the 2 times. Next 1 1 means the assumption either it may be 0 or 1 means this assumption. So here the thing is that here something is different. Here first we are making itself the assumption, right? So then we are finding the output value, right? So once it is done, next we need to find the final operation, right? So let me rewrite quickly so that you will be understanding. See, so this is the table I have considered here, what we explained exactly in the few seconds back, right? So now, so again you don't need to pass this qn value here 0, again qn value equal to 1, then pass the input value, no need to find out, right? So if you understand this concept perfectly, the same table we can copy to here, right? So first see that what is the input value here, 0 0. What is the meaning of 0 0? No change. So what is the meaning of no change means, now we'll see what is the meaning of no change or memory operation. So no change or memory operation means if previous output, right? So previous output is something 0, the next level output also 0 only, right? So memory means it will recall the previous value, that's it, right? So in memory statements or no change statements, the next state value equal to, the previous state value equal to next state. It means that previous state equal to 1, next state also 1, previous state equal to 0, next state also 0. It means that it is recalling the same information back when input condition equal to 0 0, right? Now we'll come back to here. So what is the condition here, 0 0, right? So 0 0 means what is the condition, no change condition, right? So 0 0 means no change condition. So what is the output value, try to guess. No change means this is the first level, right? This is the previous output, this is the next level output. Qn plus 1 is the next level, qn is the previous level. So 0 means what, 0 only, because no change means previous output equal to next level output. So 1 means it will be 1 only. So this is what we called as the no change or memory state. The same thing they have written here. 0 means 0, 1 means 1, no change or memory state. So once it is completed, next what is the input condition, 0 1, right? So what is the meaning of 0 1? So if you see that this is the 0 1, right? So 0 1 means what is the condition, reset condition. So what is the meaning of reset? As I explained multiple times, reset means whatever the input value you will be getting, the output value should be always 0. It means if you are giving 1 also, output should be 0. If you are giving input 0 also, output should be 0. This is what we called as the reset condition. Always output should be 0. That is what we called as the reset condition. Now which one is activated, 0 1, right? 0 1 means what condition, reset condition. So 0 1 means reset. Reset means output should be always 0. So see that when reset condition is activated, if input is 0, what is the output value, 0. If input is 1, what is the output value? Yes, it is not 1, it is 0. Reset means output should be always 0 only. This is what we called as the reset state, right? Now come to here. So what is this state, set state, right? 1 0 means what, you don't remember this one you don't remember. If you remember this one, then something is very easy. So 1 0 means what we have done, set state, right? So what is the meaning of set state? If s equal to 1 means, right, if set is activated means, so if you are giving the input something 0 or 1, what should be the output value? So set means output value should be always 1. And if you are giving input equal to 0 or input equal to 1, output should be always set. Set means output should be representation with the 1. So it means that either you are giving 0 output equal to 1, 1 means also 1. So it is means set. This means 0 means reset, right? So for 1 1 condition, what is the output we got here? For 1 1 condition we got invalid. Invalid means either we don't know what is the exact operation. So this can be represented with the cross mark. So we don't know here, we don't know here. So it means that it is invalid, right? If you see that the same concept here we applied here, right? So why we need to draw this truth table means, then if you are going to convert one flip-flop to the another flip-flop, then this table is required, right? So if you want to write the excitation table, something application table, then also this table is required. So I think this concept is pretty easy to understand. If you understand this one, the same concept you copied over here. So from this we can find out the characteristic equation, excitation table, truth table, everything. So now what we will do is, we will try to draw the characteristic equation, right? Characteristic equation for SR flip-flop, right? So for SR flip-flop we will try to write the characteristic equation. First we will try to understand what is the meaning of characteristic equation. The simple meaning of characteristic equation means, either if you pass this truth table value into the logic circuit diagram, we can able to find out the output Qn as well as the Qn bar, or something we are finding some expressions, right? S bar, R bar, Qn plus S Qn bar, something. Or just after finding this logic expression, if you substitute this value into this expression, automatically you will be finding the output values of Qn as well as the Qn bar, right? It means that one way is that you pass the input value into the circuit to find the output value, or same input value we want to pass into the logic expression, so we'll be getting the same output expressions only, correct? So now we'll try to find out what is the characteristic equation for the SR flip-flop, right? So first, if you want to find out the characteristic equation, as we discussed multiple times, what is the requirement? The first one is, so from the truth table only we need to find out. So from truth table what we have to do is, we need to find out the minterms. So minterms is nothing but the SOP function. Once it is finding the SOP function, you will be finding the minterms value. So after that we need to represent the K map for that particular minterms. Then we have to perform the minimization operation. Once it is completed, then finally you will be finding the logic expression, right? If you do these three things, then characteristic equation is completed, right? So first, what is the truth table we can consider? So we'll consider this truth table, right? So we'll consider this truth table operation, right? Now see that what is the input value? SR Qn, right? So let me write 0 0 0 means what? 0 0 0 1 means 1. So 2 3 4 5 6 7. So how many outputs we have to find out the minterms? See that we have only single output. What is that value? Qn plus 1. So what is the meaning of SOP function? Representation of the output equal to 1, right? So representation of output equal to 1 is we called as the SOP function. So where to find? Here find out how many SOP values are there. This one is there, right? What is that input value? The input value is nothing but 1, right? So next, what is this one? The input value is nothing but the 4, right? 1 comma 4. Next, this value is the 1. So what is that value? The value is the 5, right? So SOP function we got as the, right, for output Qn plus 1 we got the minterms of, right? So 1 comma 4 comma 5 comma 1 comma 4 comma 5. But here one more important point to be remember is, we will be having the don't care combination. Why don't care combination means, this is either we don't know this value is 0 or 1, right? In case if it is 1 we need to consider, right? If it is 0, that is okay. If it is 1 we need to consider, right? It means that either we don't know this value 0 or 1. So in this case we need to consider the don't care combinations also. What are the don't care combination? For input value 6, for input value 7. So after finding the SOP function, then we need to draw the K-map. Now try to identify which variable K-map is required, 2 variable or 3 variable. As we know that how many number of inputs we have, right? So how many number of inputs we have, based on that particular variable K-map we need to consider. If we see that how many inputs we have, 3 inputs, right? 3 input means we need to consider the 3 variable K-map, right? So let me take 3 variable K-map, right? So what is the first input value? S, right? So here I will take S, here I will take RQN, right? S bar, S, R bar, QN bar, R bar QN, RQN, then RQN bar, right? So once it is done, so we'll write the minterms value 1, 2, 3, 4, 5, 6, 7, right? So what is the minterm we got? 1, 4, 5, right? 1, 4, 5. What is the don't care combination? 6 and 7. So 6, 7, right? So now find out the logic expression for output Qn plus 1, right? So what is the logic expression? Try to find out. So this is, we can group, right? Don't care is here is helpful, right? So expression is S plus. So this is something like this, right? S bar S cancel. So finally it will be R bar Qn. It means that if you pass this value, so what is the input value? 0, 0, 0, right? You just pass this expression into this one, then you will be finding output this one, right? So that is the meaning of the characteristic equation, right? So what are the things that we have explained here is, in this today's session, block diagram completed, then NAND logic expression is completed, then SR flip-flop designing, then operation is completed. The one more equivalent truth table we have designed. From that equivalent truth table we have obtained the characteristic equation, right? If you understand this concept, then remaining flip-flop is nothing, right? Only simple modifications will be there, right? Now we will try to discuss the what is the limitation of the SR flip-flop. This is important, right? So limitation of SR flip-flop or drawback of the SR flip-flop. Now if you understand here, for 0, 0 input it is producing the output, right? It means that it is giving some memory operation, right? For 0, 1 also we are getting the output. For 1, 0 also, see, for 0, 0 we are getting output. For 0, 1 we are getting the output. For 1, 0 also we are getting the output. For 1, 1 we are not getting any output. It means that instead of getting the output waveform either 1 or 0, we will be getting something like this. In this duration of the time period, we will be getting the invalid or indeterminate state, right? So this is not expected, right? So the reason, either you can get the output value equal to 0 or 1, but here we are getting the impedance state, right? Invalid output state. It means that in practical application, SR flip-flop will not be useful. Why SR flip-flop will not be useful means, when input condition equal to S equal to 1, R equal to 1, we are getting the invalid or indeterminate operation, right? So now where we can use the SR flip-flop means, if something you don't have the input is 1, 1, then we can use the SR flip-flop. The drawback of limitation of the SR flip-flop is, when S equal to 1, R equal to 1, it is invalid state, right? So to overcome this one, next we are going to design something called as the D flip-flop operation. So if you think that if this condition is satisfied, it means that either you are getting 1 or 0 on something, then we don't require to learn the D flip-flop, right? So in the next class we are going to learn the D flip-flop operation. Remember one important point is that, so here S equal to 1, R equal to 1, then only we are facing the problem. This can be solved by using of the data flip-flop or delayed flip-flop, right? So for that reason we are learning the one more basic memory element, nothing but the data flip-flop, delay flip-flop or D flip-flop operation, right? So if you understand this SR flip-flop operation, then D flip-flop is nothing. Thank you very much, guys.